part 2 of the machine learning tutorial for material science using the Python programming language, prepared by myself, Sharif Abdul Qadir Tawfiq Abbas, and that's my Google Scholar profile. Okay, so this page here, that's a Google Colab notebook, which is written in the Jupyter language. I'm just gonna be sharing that screen here, or that link to you, so that if you haven't had a chance to get that one, that's a public page. You can actually download that page. You can convert it to a PDF. And the cool thing about this page is once you download it and then upload it into your own Colab account, everyone can get a Colab account if you have a Google account. Then once you do that, you can actually start running Python code within the notebook. Now, we've covered a few bits about this, and I've talked about how this notebook works and how you can get access to these Colab notebooks. And we also covered bit of Python in the last tutorial. That's part 1. I think it was a couple of weeks ago. So we had an overview of machine learning in material science, discussed a bit about Google Colab, basics of the Python programming language. That was a very quick overview of the Python programming, just bits of syntax to help us through these, to understand what's going on in these tutorials. And then one of the very important material science resources on the internet, which is a free resource, the Materials Project database, which hosts at the moment more than 120,000 inorganic crystals and a lot more crystals of other types like porous materials and alloys. We will be in this tutorial. We will be focusing on the the inorganic crystals, and that's what we discussed in the last tutorial, how we can access inorganic crystals and their properties via the Materials Project database. And then how we can interact with the Materials Project database using Python. So we had to download and install the PyMatGen Python library. And the cool thing about all these tutorials that I'm doing is that all of them can actually be done over the notebooks, the Colab notebooks. You don't even have to use Python on your computer. I have engineered these tutorials in a way that you can run all of these exercises and write your Python code just right into the browser here, in these notebooks. If you want to, do further work, do more intensive applications, then you can definitely, it's much better to do it on your computer. But just for starting to learn Python and doing these machine learning activities, it's just sufficient to use the Colab. That's the Colab I'm talking about. And then querying structures using PyMatGen. Now today we are going to discuss what's building on what we did last time. We're going to be discussing further details related to creating the dataset and you doing machine learning on the dataset, predicting a specific quantity of interest. What we are interested in today is to predict the band gap, in EVs. This information is already available on the Materials Project dataset, and we will be using this information to train machine learning models and then use those models and predict the band gap. It's going to be a very cool exercise. There will be a little bit of tweaks that we will learn how to create data sets, how to pre-process. So the few steps here. First of all, we'll discuss descriptors. What are descriptors? And then we will be building simple descriptors for data set. Start building the data set. There's some code, Python code, to build an actual data set, almost 4,000, a bit more than 4,000 materials. And then doing actual machine learning on data set. Accuracy won't be our biggest thing today in terms of predicting. We won't be making very, very good predictions, prediction accuracy. I think someone is saying that they are not seeing the screen. Is that the case, everyone? Are you having trouble with the sharing?
Yes, it seems like everybody has.
Okay. I think I made a stupid mistake. Sorry about that. start sharing. I switched off the sharing by mistake. I'm sorry. Yeah, it was my bad. I stopped the sharing. I mean, Skype should have warned me that I was doing this. Okay, I believe that you guys now can see my screen. Okay, so that's the plan for today. Now let's get going. Okay, that was part one, bird's eye view, blah, blah, blah. And then we did a lot of Python, 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 Python lists. By the way, Python lists, it's really important to understand what lists are. That's like an array of, or a collection of things. These things could be numbers, could be strings, and that's an example of a Python list. We will be making use, a lot of use today with Python lists and loops. So we will be using those two in our machine learning exercise. Getting cool. Let's keep going. Let's keep going. Loops, loops, loops. All this material is here available for everyone. I didn't want that. Okay. And then that's the material project page, accessing carbon, like that's the diamond structure. Blah, blah. PyMagen Python library. You can just install PyMagen just by typing this line here in your materials, in your Colab. Boom, boom, boom. Da-da-da. Structure file form. We discussed the CIF format as well last time. And then we opened the CIF format and then started looking at its content. That was a zinc, ZnFe, some alloy of zinc and iron, and then extracting its information, blah, 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 blah. And then we had a look at querying structures using PyMagen. And remember when I told you the API key thing? So to be able to query structures in PyMagen, you've got to have your own API key. It's a secret. So I'm going to have to, look, I'll leave it here. I'm going to change it later. It's a secret key that allows you to make queries to the materials project database. Everyone should have their own PyMagen API key. You can get it, it's for free. You can just go sign up using your Google account, any account, and then you can get that one. Okay. May I just ask as well to make, in order to, may I just ask if everyone please just switch off your mics, your microphones? Okay. Now, Okay, now last thing we did was making a query for materials based on the band gap value. So I want all materials with a band gap that is, GT means greater than 6 EV. I want the properties which are a material ID. We found 815 materials. And then these are the IDs of the top 10, like the first 10 in the list. Okay, so that's all for the last part. Now let's move on to the new stuff. Let's get going with some machine learning. The first thing that you want to do when you want to do machine learning is, what is the data set? So the data set is a lot of data. And the task in machine learning is to predict something, predict some unknown values based on some known values. I mean, if we go back up here to this, where's the workflow or the flow chart? Yeah, that's really the an overview of the whole process. You have a data set. The final output that you want is to predict a particular quantity in that data set. I'm talking about, for example, you have thousands of materials. Each material has got its own, let's say, atomization energy, people in chemistry, HOMO-LUMO gap, chemistry people, band gap, material science people, whatever. I mean, you name it. So these quantities, it takes either a lot of calculation to obtain, these like the band gap, the atomization energy. It takes a lot of calculations to obtain these properties. So you want to use machine learning in order to obtain them easily. You want to calculate the EV, the band gap, without having to do a lot of DFT to calculate the band gap, because DFT sometimes costs a lot of resources. You don't have those resources available, for example. Or if you want to predict the band gap for thousands of materials, which is impossible if you're going to do DFT for that. Or if you want to actually predict the band gap, and even without DFT, you're an experimentalist, and you do experiments to measure the band gap, but you don't want to keep measuring the band gap for thousands of materials. So you use machine learning to predict the band gap instead of having to measure the band gap every time. That's the cool thing about machine learning. A huge, massive time saving in terms of predicting properties. So the first thing that you want to do with your dataset is to identify descriptors. Each item in your dataset has to be defined in terms of descriptors. Let's say, for example, you have thousands of molecules, and those molecules, like let's say those are actually not molecules. Let's just say these are dyes, and you want the homolumo gap for these dyes. So each one of those dye molecules has already a measured band gap. Let's say there are 1,000 or 2,000, right? But then you want to be able to predict the band gap instead of having to measure the band gap for the dye molecule. You want to predict the band gap for thousands of other dye molecules that you don't even have. So the first thing is, for each dye molecule, identify numbers that can describe the dye molecule. So here's the material that you have. This could be a 2D material, a crystal, a dye molecule, a car. It could be anything that you want to study in your data set. And then you're going to extract descriptors for that thing to describe this thing uniquely. It's very important. This uniqueness is a very important concern. And I'm going to go into a little bit of detail about this uniqueness issue. So the first thing is numbers to identify this thing. So the numbers for a TV could be like the inches. That's the TV. Let's say we have thousands of TVs, and you want to do machine learning on them to predict some quantity based on the TVs. So if you want to describe the TVs, so I have an Excel sheet. The columns are the inches, the power, the current, the voltage input, the frequency, blah, 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 and then some other descriptors that relate to the electronics in the TV, whatever else. The descriptors are quantities that will be describing every single data item in your data set. Every single material, every single molecule, every single crystal, it has to be applied for all of them. Because eventually, when you're creating a data set, you want to see an Excel sheet. An Excel sheet that looks like this. It has, the rows are the materials, material 1, material 2, material 3, and the columns are the descriptors. So that is the data set that describes the data that you have. Descriptors describe each material. You have the same number of descriptors. Actually, the same descriptors have to describe all of those materials. Of course, if you have two materials with the same descriptors, that's going to be a bit of a problem, right? Because this means that there's a repetition, maybe. So this means that those two materials cannot be described uniquely because the same descriptor is describing both materials. Maybe you have one material is some dye molecule and the other material is another dye molecule, or this material is carbon, it's calcium carbonate, some crystal phase of calcium carbonate, and this other material is another crystal phase of calcium carbonate. If those two different materials are described by the same values for the descriptors, this means that we're putting garbage into this brain here. The next stage is the machine learning. This is a brain that we're going to teach. You're basically telling this brain, hey, Tim and George are just the same thing, but I still want you to predict different properties for Tim and George. But the brain is going to tell you already told me Tim and George are the same thing. How would I know? Descriptors must give unique values for each material. That's a very important concern, and it's actually one of the complications when we deal with material science descriptors. In chemistry, it might even be a little bit easier to arrive at descriptors than in material science. So I'll go into more details about this now, actually. Now that we're here discussing descriptors, let me actually show you something. If you want to describe, let's say, a molecule, I know that a lot of people coming in here are already, desiring to see a lot of coding and stuff. But remember always that machine learning and data science is really a science. So there's a little bit of stuff that you need to think about and learn before you actually start coding. So now let's just visit this topic of descriptors a little bit in detail. There's a lot of write-up that I wrote here. I'm just going to be skimming through it as I discuss, but you can read it on your own later. So we want to, the first question is, how do we apply machine learning to predict crystal properties? We want to get descriptors. Now, if you want to describe a crystal, okay, and usually you want to use descriptors that are not time consuming, that do not require a lot of measurements, because if you use descriptors that come from measurements, it really defeats the purpose of machine learning. Machine learning, you want to do machine learning to save time, to save measurement costs or time, computation time, right? So you want a descriptor that is describing the material based on the basics of the material. Here I mean, for example, the atomic structure of the material. So you get from, if you want to predict the band gap, for example, of diamonds, right? We want to describe diamond in a very simple, using descriptors that do not require us to do any calculations, any DFT calculations. So we just use the atomic positions. Let's just use the atomic positions of the carbon atom in a unit cell in diamond. But the problem, if we use the atomic positions, let's say that we have how many atoms in a unit cell? 1, 2, 3, 1, 2, 3, 4. And I just put one here, extra. So basically there are 4 atoms in the unit cell of diamond. So this means that that's 4 times 3, because each atom has 3 coordinates, right? So that's 12 numbers, X, Y, Z for the first atom, X, Y, Z for the second atom, and so on. But there's a big problem with this approach. The problem is the unit cell of diamond, it already belongs to the crystal of diamond, right? So here's the unit cell. It belongs to a crystal of diamond. So it's like the repetition, infinite repetition of the unit cell of diamond in all 3 directions. If you want to use the atomic position of the atoms within the unit cell, we get into an ambiguity here. The reason is, you see, I used this as a unit cell for diamond, structure for the unit cell for diamond. It has its own X, Y, Z coordinates. But then you see, this is also a valid unit cell for diamond. And obviously here, the X, Y, and Z values for each of the atoms is completely different from the X, Y, and Z values for the atoms here. This means that the same unit cell is describable here by 2 different sets of descriptors. I mean, in fact, it can be described by an infinite number of ways. You can, not infinite, I mean, let's say a vast, how many? I cannot really count them at the moment, but a large number of possibilities. This means that the descriptive value is not unique. One diamond unit cell can be described by several different ways. Non-uniqueness of descriptors is very misleading to machine learning. What you need to do is diamond, no matter what snapshot you take from the diamond crystal, how the unit cell of diamond looks like, it has to be described by the same numbers. This means that the unit cell, the descriptors of diamond must be invariant with respect to the atomic positions within the unit cell. This invariance issue is not a problem with molecules. That's why I was saying, in chemistry, it might be a little bit easier. There's another blog post here that predicting the homo-lumo gap. Just open this one. In this blog post, that's another exercise for a machine learning exercise where we arrive at descriptors for molecules, just plain old molecules. A data set that has 134,000 organic molecules, and then predicting the homo-lumo gap. To arrive at descriptors for these molecules, we don't have this periodicity issue. you know, like in a crystal in diamond, this unit cell is repeated. So the X, Y, and Z values for the atoms might take many different values. Here, in the case of like just a molecule, like a dye molecule or whatever, you can actually find out ways to obtain unique descriptors based on the atomic position, and that's called the Coulomb Metrics. You might like to have a look at this tutorial as well. The link is up on the on this notebook instead of having to open many different things. So the link is up here. So there's this Coulomb Metrics which can might a little somehow do the trick in terms of offering you a set of descriptors, to uniquely describe the molecule. There's a huge amount of research just on the best way to describe, to calculate the Coulomb metrics. With material science, there is currently a lot of research on how to determine a set of numbers or descriptors that can uniquely describe the crystal, given that the crystal has this translational issue. It's the translational symmetry. If you move the unit cell this way, for example, you can get a unit cell structure that's completely different from the original one. It's translational, there's translational symmetry. So it's not easy to just obtain information or descriptors about the structure just from the XYZ structure of, the unit cell. And because I don't like to keep going, talk, and losing people's attention, losing people's concentration, I just wanted to be sure, is anything I've been saying here not very clear, complicated? Do you want me to explain anything again? Are you okay so far with this stuff? Is anything that's not 100% clear? You can type, you can message me here if you want. So far, so good? Awesome. Okay. Perfect. Okay. So we want to arrive at descriptors that are invariant with respect to the translation of the unit cell. Okay. Again, if anything is not 100% clear, you can just still go back to the discussion. I've written a lot of text here that hopefully can clarify a lot of things. Okay, so if you want to build a descriptor, a unique descriptor for each crystal, you might like to consider a different approach. Instead of just focusing on the atomic positions, how about this? Let's say we have a crystal of like zinc and Fe atoms, zinc and iron atoms. Instead of focusing a lot about on the geometry of the crystal, how about this? How about talking about averages or statistical quantities involving the atoms within the crystal? So, for example, you can start creating a set of descriptors for the crystals based on the average of the atomic numbers, or the average of the ionization potential of the atoms, or the average of the electron affinities of the atoms, and so on. And that's just the averages. You can also expand this and start using other statistics: minimum, maximum, standard deviation, and variance. These are all numbers that statistically describe all the atoms within the system. But it's obvious that these numbers are not really sensitive to the actual nature or the actual structure of the crystal. It misses all the beauty of what you see in diamond crystals, for example. So actually, there's also there's a bit of problem here in this approach. If you just do these averages and standard deviations of atomic properties and completely ignore the geometry, we get into a problem when you have a crystal and it's polymorph within your data set. Here I'm discussing this bit here. There are 27 possible structures for SiC, for silicon carbide on materials project, just silicon carbide with this same stoichiometry. This means that there are 27 structures that could have the same averages, right? Because they all have the same number of atoms within the unit cell. So this means that we need to start adding more descriptors that relate to the atomic structure, to the geometry. But what sort of geometrical descriptor? Let's think about this. First of all, let's do a little bit of Python here. So in the materials project, remember up here when I obtained when I queried, or when I this exercise, you guys remember this crystal here, and then I got it from some folder on my blog, and then I saved it as a structure object. So structure equals parser get structures, and then print structure 0. So that's the only structure in the lists. So that's the first one. So its index is 0, and then that's the structure I have, zinc ZN18FE8. Now let's take this structure and apply the descriptors calculation I just described. So here, that's the first bit of Python coding that we're doing. We want to calculate the mean, maximum, minimum, and standard deviation of the atomic number. Remember when I said the atomic numbers? So the atomic numbers of the atoms within the crystal. So here we have ZN9F8. What is the mean of the atomic numbers? We calculate the mean, and then we save it in this variable. Let's just run this thing. Oh, it's not defined. Oh, I have to. Oh my goodness. Okay. I'm just gonna have to rerun things. Okay, thank you very much. Just give me a second, please. I'm gonna have to rerun some stuff here. Seems that my Google Colab notebook forgot some of the things I installed. And because of that, I'm gonna have to rerun things. I think this is done. Yeah, installed. Just takes a minute. Come on, come on. Yeah. Okay, still downloading. I thought Google would be much quicker. There you go, I think. Okay. And then that's so I'm just yes, it's all good now. It's all successfully. So I see successfully installed blah blah blah. That means it's ready. Now let's run this thing. So here I'm opening this CIF file on my blog, and here I'm going to print out the structure, and then here I'm going to print out some of the things in the structure, like the lattice vectors, the elements, the total charge, or the species and total charge, Cartesian coordinates of the crystal, and the atomic numbers. Now, what we're doing here now is to get the mean of these atomic numbers, the maximum, the minimum, and the standard deviation, and then use these as invariant descriptors. So if I go and run this little bit of Python code, boom, there you go. You see these numbers? These are our first descriptors for today. So we have 4 descriptors for the crystal based on the mean, maximum, minimum, standard deviation. As you can see here that I had to import NumPy. NumPy is a very popular, massive mathematics library in Python that enables us to do a lot of really cool Python mathematics stuff in Python. One of the richest numerical libraries, I think, in the world even. It's really cool. Does a lot of stuff very efficiently as well. It has np.mean, means I'm accessing the mean function within np or within NumPy. Import NumPy as np means I want to import NumPy. I'm gonna give NumPy an alias, the alias being np. So I can just refer to it as np instead of having to type numpy.mean, numpy.max, just np.mean, np.max. Now this is a list of numbers. So the mean of the list of numbers, that's the number I got here. Okay. So far, so good. Now, I talked about the uniqueness of the descriptors. So I've got a descriptor set here of 4 numbers to describe the crystal. We need more descriptors. And I discussed this polymorphs thing, the 27 polymorphs of silicon carbide. So we need descriptors that relate to the structure. One of the really, really cool things that PyMagen provides is that it gives us the distance matrix for the lattice. And the distance matrix it's a matrix. The size of the matrix is the number of elements by the number of elements. And then this matrix is basically the distance between, or the nearest distance between every element and every other element, taking into consideration the periodicity. This means that this carbon here, the distance between this carbon here and that carbon, you see that carbon I cannot see here because that's the unit cell, right? So in the crystal, there's going to be a carbon right here, and there's going to be some carbon here, some carbon there. So the distance matrix gives me the distance, all the distances between all the neighbors. So that carbon and that carbon, that carbon and that carbon, each carbon and all the surrounding 4 carbon atoms. Okay, that's the distance matrix. It's very super useful. So I was thinking, okay, one maybe easy way to obtain unique descriptors based on the distance matrix is just to do the same thing. Get the mean, max, minimum, standard deviation. Even though the distance matrix is a 2x2 matrix, it's a 2x2 array, so it's a matrix, mean is going to calculate, again, the average of all the values in that matrix. It is going to recursively visit every number and then obtain all the average of all those numbers. So those are our next 4 descriptors. Let's run this, and these are the numbers. Okay, the minimum is 0. I'm not exactly entirely sure why that is the case, to be honest, but let's just take it as it is. That's the standard deviation in the distances. Yeah, 0, of course, because in this matrix, the distance between the atom and itself, so it has to be 0. Of course, this has to be removed at some point, but don't worry about this for now. Okay, 0, and that's the maximum distance between 2 carbon atoms within the unit cell, and that's the mean distance, and that's the standard deviation. So I'm just still using PyMagen to obtain all these descriptors. So now I have how many descriptors? I have 4, and I have another 4. So that is 4 and 4, like 8 columns in my data set so far. Okay. So I have some descriptors, an idea to obtain descriptors using Python and PyMagen and NumPy, of course. Now let's move on to the serious stuff, to actually building the data set. This is a 2-step process. First, we need to collect the data set. We need to collect our structures, and then we need to pre-process the data. Why do we need to pre-process the data? It's going to be very clear in a few minutes. So to collect the structures, again, thanks to PyMagen, we can use the query method in PyMagen to query many structures subject to certain conditions. This is a very useful line here. You might find it really useful. Here I'm querying all of these structures that have the formula A, B, C, 3. And this can actually might remind us of perovskites, right? That's the typical formula for a perovskite structure. So this is going to give me 4,291 perovskites that are currently available in materials project. So when I run this, let me actually run it. Oh, okay, of course. I'm going to have to rerun something. What is it? Yeah. I have to run this so that this M is defined, and then I can just go here and run this again. Okay, it's going to take a little, just a few seconds. And here are my 4,291. You know what? That's the data set, but it still needs some work. This data set is just the structures, the CIF files. You see, I'm requesting CIF files and requesting band gaps because I'm actually interested in predicting the band gaps for those CIFs. Now that I have the CIF files, let's use the code that we used above to process the CIFs and extract the numbers that we need from them. So we are going to go and fill some lists with numbers. Now think of the columns that I discussed. We have mean atomic numbers, I'm going to create a list of mean atomic numbers for all the 4,291 structures. And I'm going to initialize this list as a blank list. The same thing for the max, min, standard deviation. I'm also going to, soon I'm going to discuss the lattice parameters. We also can use the lattice parameters. There are only 6 lattice parameters that we can add to the data set. The A and the B and the C, alpha, beta, gamma lattice parameters. These are lists or the columns for those parameters, and then the distance metrics statistics. So that's how many? 4, 4, and 6. That's 14 descriptors for each of our materials. And the band gap, so initializing the band gap list here again with a blank list. Just to show you how the lattice parameters work, these lattice parameters, here I'm printing out the lattice parameters for our ZN9F4 lattice. So the way to do it is that that's the variable, the variable of the lattice object, and then dot lattice gives you access to the lattice object within it, and then ABC, that's a tuple of 3 numbers, the A and the B and the C. So if I just run this code, I'm going to get A equals 7, blah, 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 B equals 7, blah, 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 C equals 7, blah, blah, blah. So these numbers here, these are the lattice parameters in angstroms, and the alpha, beta, gamma in radians, right? Okay. Now we are ready to actually create our data set. I'm going to run this code. This is a for loop that is going to iterate through all the results. In every iteration, it is going to do the following. It is going to extract the CIF, convert the CIF using this line here, these lines here, convert the CIF into a CIF structure object, and then using the structure object, it's going to get us the atomic numbers, lattice, and the distance metrics, just like we did above. This is going to be iterating for how many? 4,000 iterations, 4,291 iterations. And eventually it will give us lists. How many lists? 1, 2, 3, 4, that's 4, 6, 4, and 1, that's 15 lists. Next step is going to be, we're going to be using what's called pandas, data frame, to take all those lists together in one sheet. Let's consider this as taking all those columns together, and we put them together all in one, like a sheet. It's called data frame. I'm going to discuss this in a second. I'm just going to run this. It takes a few minutes. While waiting, let me see if all good so far. We're waiting for 2 minutes anyway. Cool. Sorry, but my keyboard is giving me a headache here. No worries. No worries at all. Okay. So where does it? Oh, it's still running. It's a loop that is looping through all of the 4,000 structures, extracting, converting them, extracting all these numbers, and putting them all. Now in Python syntax, you see this is a list, right? Plus equal means mean atomic number is equal to the mean atomic number plus this list item. So eventually I'm getting mean atomic number list, a larger one, because I've just added another element, and another element, and another element, 4,291 elements. Same thing for the rest of these guys. Now BG here, that's the band gap. I got the band gap using this line. Now where CIF and band gap strings here are coming from, they're coming from the query that I ran here. You see, properties, CIF, band gap. These are going to give you a large string or a dictionary, and that dictionary has got these 2 keys for each structure in the dictionary, the Python dictionary. Okay, next step is, let's actually, now that we got all the numbers, let us look at the numbers. Let us do some data visualization. That's a very important exercise to spot if you have any outliers, if there are, what's the distribution of the data, if there's any hypothesis testing that you want to do. Okay, I'm just going to do this very quickly here. So that's, I'm using the matplotlib library. in Python to do the plotting, just those few lines here to plot a histogram. We don't have enough time to go through each one of those lines, but you've got them here. You can just copy paste them and use them, and then you use the Google, the cool people on Google, to answer any questions related to these lines. So if you, for example, you want to plot a scatter plot, you can just go on Google and type matplotlib scatter plot, and then you will find a huge amount of resources and Stack Overflow resources. So what I'm seeing here in this plot here is that at 0, there are more than 2,000 structures, and the rest, that's the rest of the 2,000 of the 4,000. So half of the structures have a 0 band gap. You see the x-axis is the band gap, and that's the count of structures. This means that half of our data set are metals, 0 band gap. Whether this is an outlier or not an outlier, it depends on what you really want to do. It shouldn't be an outlier because you want to predict the band gap for both for metals and for semiconductors. But we've got probably what can consider as an outlier here, around the 7 EV, because it's a bit far away from the 6. But anyway, I'll just keep going with this data set. Let's also have a look at, do a scatter plot of the data set. So I'm going to sort all the band gap numbers here, and then I'm going to plot, plot, and then those sorted band gap numbers. So what I have here is that the y-axis is the band gap, the x-axis is the structures. That's 4,291 structures, right? So we have half of them have 0 band gap, and then the band gap increases almost linearly until very few structures have very high band gap. That's why I was saying there could be some outliers. Now let's keep going. Okay. Let's put the data in a data frame. Remember when I talked about the data frame or the sheet where we collect all the data together? That's what we're going to do here. Data frame, that's an object or a class in the pandas, in Python. Pandas is probably one of the most famous Python libraries that people in data science and data engineering use. It has got really cool and very rich set of tools to enable you to convert data from CSV file to a format you can deal with, to perform a lot of queries and operate mathematical operations on data. It is a versatile, really rich library that I advise you to go ahead and read about. We are also going to be using sklearn, so the machine learning library in Python, one of probably one of the most famous and the most accessible and easy to learn machine learning libraries in Python. That's the sklearn. People can argue. I mean, there are a lot of debate. There's a lot of debate about which machine learning library is the best. There's PyTorch. There is Google's TensorFlow, and there's sklearn. These are probably the most famous. But sklearn, I mean, it's beyond doubt that sklearn is the easiest one to deal with. sklearn and pandas, they really dance together. They are made for each other. The pandas data structure can easily be incorporated into machine learning tasks within sklearn. By the way, sklearn stands for scikit-learn. It has a website that's fully documented, has a lot of documentation, and a huge online community. Same thing for pandas. Okay, so I said that we're going to be converting our columns into a sheet. That's the data frame, and that's the syntax how we can do that. So we dataset underscore df data frame. That's just a variable name I gave it, equals pd.dataframe, because data frame object belongs to the pd, the pandas library. And then you open parentheses because we're defining a new data frame, and then open, and then we put a dictionary here that's surrounded by curly brackets. And then this dictionary has got key value pairs. The key is the column name. Imagine this is an Excel sheet. That's the first field, second field, third field, and so on. Remember what this was? That's the list that we created in the big loop up there. So we're putting this list into this key. So we're basically creating one field in an Excel sheet. I mean, I'm going to call it Excel sheet because it's easy to imagine this as an Excel sheet. And that's the next column in an Excel sheet, and so on and so forth. Now, one of the important things to do when you're pre-processing your data, you don't want to have a column, for example, with numbers like in the millions, and another column with numbers in the gazillions, and another column with numbers in the 0.0001, range, because this is going to be, create a tragedy in your machine learning activity. No space now to discuss all these theoretical details, but a very important thing to do with your data is called standardization or normalization. And the code to do this is just these two lines of code here. You need to fit your data to a scalar, or let's say a normalization routine. And I chose this one. It's the simplest one to deal with. The standard scalar is documented online. You can look it up, what it means. And then after fitting, transforming your data set into a new data set that has been scaled. So all of your numbers are going to be within, at the same range of numbers. You won't find, really high, unusually high numbers in your data, because, as I said, it's going to skew the machine learning algorithms. Some of the machine learning, actually almost all of the machine learning algorithms that you will be using. So that's these two lines. That's a very important task. Okay, what's that? Yeah, I'm gonna delete this. It's unnecessary. Sorry about that. So after this is done, play this. And so here we've created our data frame, and we've scaled the data, successfully finished. Okay, we're getting really close to the big deal here. Now we have a data set. That data set has scaled data set data frame. That's the like the input part or the descriptors for the structure. But where are the band gaps? Remember, the band gaps are here. That's the band gaps. Sorry, the band gaps. That's the list that we created in this array, in this loop. So we've got inputs, that the data set we created and standardized, and outputs, the band gaps. Remember, the band gaps are usually called the target vector, or the numbers that the target of our prediction activity. Okay, so now that we have the data set composed of the scaled data set df, that's the scaled or the normalized inputs or the structure descriptors, and the band gaps list, we want to teach a brain, right? We want to go to a machine learning brain and, hey, how about this? I'm going to teach you how to predict the band gap for that many number of structures using their descriptors, such that you give me accurate predictions of the band gap for those other structures. I'm not going to let you cheat. I'm not going to show you the band gaps for those other structures. I want to see how you predict the band gaps for those other structures. Have you noticed that I've been using words like the initial structures and other structures? In machine learning, we call them a training set and a test set. So there's a training set, which we are going to be using to teach that brain, that machine learning brain. And there's a test set that we will be using in order to test how accurately that brain can predict, or can it perform based on its training. We can add to that what's called a validation set, but not now. Maybe in a later tutorial. I'm just trying to simplify things here. So let's just stick to those two: training set and a data set. Now we want to do two things. We want to split our data set into a training set and a data set. Typically, people split them into an 80% for training and a 20% for testing. Okay. And we need to randomize them. So we don't, like, if you feed in the data set in a certain order, it's always a good idea to randomize the order of all the materials in the data set, just in case you have any sorting that you've done in your data set that can completely, invalidate the whole machine learning process. So we use this function here, train test split. What it does is it takes the data set X and the data set Y, or the inputs and the target, and then you put test size equals 0.2, which means 20%. Random state equals none. I mean, we can put some input for random state, but anyway, random state indicates that we're going to be randomizing, randomizing the order of the materials in the data set. So the output of this function is the X of the training, the X of the testing, Y of the training, Y of the testing. X of the training, that is the training set at 80%, the X part, or the input part, or the descriptors for the materials. Y for the training, that's the band gap for the guys here in this set. Sorry, Y test is the band gap values for these guys, for the X test. So there's 80%, 20%. 80% band gaps, 20% band gaps. Okay, next is the machine learning task. I will try to do as much, I will try to, clarify things as much as I can here, but there's a lot of details. It wouldn't be enough to finish, explaining every single bit here, but I'll try to give an overview and explain a few bits. The first thing is we want to install some or import some machine learning algorithms, and we want to also import measures of accuracy. I'm going to be focusing here on the goodness of fit, the R-squared score, and the mean squared error. So these guys are in sklearn.metrics. So this line here is going to import these two functions. And then I'm going to be using two machine learning brains, the XG boost regression and the random forest regression. Those two regressions. I didn't really cover this bit during this tutorial, but in machine learning, you could do either a regression task or a classification task. I've been focusing mainly on regression, so I only dealt with regression. Maybe at another opportunity, we can discuss more about classification. But it's mainly those two always in machine learning. Sorry. Only those two in machine learning, the classification and regression. So there's actually an XGBoost brain that can classify things, and another XGBoost regressor that can regress, that can determine a number from a continuous set of numbers. If you don't really pick up the idea of a classification versus regression, I would advise maybe just do a quick Google search of what these mean. These are the main primary tasks in machine learning. Quickly, just as a quick idea of what these mean. Classification, if you want to classify materials, for example. So the machine learning output is going to be 1 for metals, or let's say 1 for semiconductors, 0 for metals. So the output you get is not the band gap, it's the class of band gaps, or the color, like the color of the material, if it's blue, if it's black, if it's gray. So these are all categorical items or categorical target outputs. When you want to predict categorical outputs, this is when you do a classification machine learning activity. But when you want to predict a numerical output, this is called a regression machine learning activity. I mean, the present activity is predicting numbers from an infinite range of numbers, like the band gaps. That's called a regression. Okay, so I'm going to be using random forest. Here I'm putting input parameters for random forest that you can use. I mean, these need actually to be optimized. Obtained by trial and error. These are functions that the regressor takes. I'm not going to go into a lot of details. It's very complicated stuff, but maybe later on, or in your leisure, you can read more about regressions, the regressor and how it works, what sort of parameters it takes. But these could actually usually give reasonably accurate estimates. random forest regression actually works in a very, very fascinating way. You know, the forests or the decision trees that it randomly creates is stuff that you might like to read during your, between meals maybe, or on the bus when we go back to the office. Okay, so first we create the machine learning object. Second thing is we fit, using that machine learning object, we fit the model, the random forest model, to the input and the output of the training set. These are the descriptors of materials. These are the band gaps for those materials. So this is the machine learning bit. That's the learning, and that's the testing. This line is how we test the prediction. So the REGR, that's the random forest model I created. I'm fitting it, which means I'm teaching it using these two. And then I'm using that REGR object to predict for the X test scaled for the test set, what are the band gap values. So now I have two sets of band gap values, the Y predicted and the test. Now I want to see, are the predicted ones close to the test ones or not? There are many, many different ways to quantify the accuracy of prediction. And here I'm just dealing with those two. So the R squared was a very popular one, of course, so everyone knows, and the mean squared error. And so I'm printing out here these numbers. And then I'm plotting here a correlation test, a correlation plot for the random forest versus the original values, which were obtained with DFT from materials project. You see, I'm using the same procedure here, but I'm just changing the model. So instead of that brain being random forest, the new brain here is the XGBoost regressor. It has got its own different, attributes. Actually, it runs on very similar principles to the random forest brain, but it has its own benefits and also its own downsides. You see, the first thing is I create the object, fit, predict. Object, fit, predict. And then print out the mean squared error and the R squared, and then plot. So the result of all this is, I'm actually going to run it. In the meantime, while it's running, anyone has any questions at this? Oh, 1 second. What's wrong with you, man? Oh, sorry. Should have run this one first. Splitting, and then let's run the machine learning. It's running now. Any questions at this stage? So good? Okay, I'll assume it's all good. It's gonna take a minute or two. Oh, there you go. So what I got here is the MSE is 1.18 EV. That's huge, right? It's not so good. R squared is 0.489. Well, I mean, it's trying to predict using the random forest, but it's not really doing a great job. Whereas in the XGBoost, it's slightly better job, right? But then when you look at the correlation, these are the values that were predicted, and these are the values that we got, in the DFT from the materials project. There is trouble predicting, the band gap for metals, the zero band gap. While the original values in DFT are 0, the predicted values in random forest range from 0 up to 4, which means that it's a big error. There's a lot of trouble. It's not able to do the prediction. And that's the random forest, and the same thing with the XGBoost. So I thought, okay, how about this? Just to reward all the efforts we're doing, let's just try to improve these predictions a little bit. Okay, so what I did is I removed all the metals, okay, and I also removed the outliers, the guys at 7, above 7 EV. And that's the code that does that. So how I did this, same thing, I initialize all the arrays, and then here's the loop. What I do is, if the band gap is greater than 1, and if the band gap is less than 6, actually it should be greater than 0, and the band gap is less than 6, which means that these are materials that have band gaps between 0 and 6. Only if this is the case, collate all the descriptors. So let's run this, And once we finish this, I'm going to print out how many band gaps did we actually collect. It's going to be almost half of the previous data set, almost like for 2000 something. Now the cheat that I did, in terms of removing some of the data, I shouldn't really be removing the metals. Maybe I should be removing the outliers, but not the metals. You want to also predict the band gap for metals. There is actually a problem with our descriptors, and that's why I was saying it's a big research area, to write the correct descriptors. Your descriptors must be written in a way that they can predict, they can help predict everything, not just predict the semiconductors. Also, the metals should be predicted. So when I do this cheat, okay, and then, so here what's going on. I actually rewrote the whole entire machine learning code and ran the whole thing. Okay, there you go. So now I have 2,182 structures in our data set, which is half of what we had before. But then in the MSE, the mean squared error is, it's still high. Even the R squared is even lower now. Bad. That's quite bad. This didn't improve anything. So that's the thing. I mean, you shouldn't remove any bits from your data just to improve the R squared. You should always work on your descriptors. Descriptors, that's the key thing, to work on. I'm gonna do this again, just removing, just constraining the band gaps from 1 to 6. Let's see what we get. Okay, I'll just leave this going. It might improve things a bit, but again, this is a completely artificial improvement. What you need to improve is to improve the descriptors. The descriptors that, the 14 descriptors I created here are just for an exercise to show you how Python works and all, but what we need to do is to work on the descriptors. And as an example of really good descriptors, okay, here's what we get when we remove some of the data. Yeah, so the MSE actually is improved, 0.7 instead of 1.2. R squared is not so good, but the XGBoost gives us a better R squared, 0.52, and a better MSE, 0.63 EV. So, I mean, yes, we removed some of the data to improve the performance, but this is not the way it should be. What we need to do is to work on the descriptors. We need to come up with better descriptors to describe the data. And in many situations, you might need a lot of descriptors. Tell you what, you see this blog here, this blog post. So this blog post is about using machine learning in a recent publication of mine and a team in the United States and here in Australia. A paper we recently published using machine learning to predict thermal properties of crystals, and we also predicted the band gap in this data set. Now, what we had here in this data set that was really cool is the descriptors. The descriptors were 1,800. So we had an Excel sheet that had 1,500 materials and 1,800 columns. A lot of descriptors, including the 14 ones that I just showed you, or like variants of the 14 ones I showed you. But in addition to those, I mean, a lot more, 1,800. So if you want to do machine learning on materials, the key thing that you want to deal with is coming up with good descriptors that can uniquely describe the material, and the success or the failure of a machine learning exercise is related to the quality of your descriptors. Like in this paper here, we showed that, I mean, we used 4, I think, or 6 machine learning models. All of them had really, really close prediction accuracies. Where is the... by the way, there's a lot of code here as well. I made all the code that I used in this paper public, as well as the data set, if you want to have a look. You see, we got R squared is 0.89. That's pretty good. That was for one of the, I think that's for the entropy that we predicted. You can see here that that's the good correlation. And again, this goes down to the descriptors that we used. And I think that's all what I wanted to say today. That's it. And at this stage, and now I'm done. Anyone has any questions? Questions. Happy to spend a few minutes discussing questions, and then can call it a day, and I'll upload the video on the blog, and we'll share it on Twitter, and we'll also email you via Eventbrite. Questions? I mean, it would be a good idea also to look at these blog posts where there's a lot of code, and this is like production code, the stuff that was published. And here, this was an exercise, a very simple machine learning exercise, using a very massive data set in this, paper. It's all here. Okay. No worries. Thanks, Marine, for your kind words. Okay, so since no questions, really thankful for your all of your attention, all of you and your attention. Thanks for your interest. Have a lovely day or have a lovely night, depending on your time zone. As I said, all the code, all the video for this tutorial will all be shared. Okay, see you all. Deep learning and machine. So deep learning is just machine learning using deep models. In machine learning, you've got neural networks, for example, one of the models. A neural network could be a shallow neural network, one hidden layer or two hidden layers, or it can be a deep neural network with many hidden layers. So deep learning is just machine learning using deep neural network or many hidden layers neural network. People make a buzz, out of it, but it's not really, nothing is very special about deep learning, except that the models are very complicated, like very large number of degrees of freedom, or number of layers in the neural network. Okay. Just stop recording.